Hello YouTube, De-bodgery here. Welcome to EV Components Review. On the bench is the dissected Moto FSPEC motor. Mark II. It says it right here. See that? MK2, whatever that's supposed to mean. So there was a FSPEC version Mark I. I don't know. Saw that on there, I thought, okay, yeah, must have been a second revision of it and fixed some stuff because it was really awful. I don't know. And made it less awful or something. Yeah, your guess is as good as mine. All right, so let me talk about some things that I have found. Some good, some not bad, and some bad about this motor now that I've had it apart and had a chance to inspect a little bit more. So, as is not unusual for Moto, they try to make things pretty on the outside, and this is a fairly common way of doing things in China. Make things pretty on the outside and skimp on the inside stuff. And, well, they have. So, like on the inside of this cover, yeah, you can see it right in there. So you can see how this little like rib going over here has got kind of like a little shoulder over there. Whereas like if you look at these ones over here, they have like a very uniform T-shape to it. So yeah, this one here is like, yeah, who cares? You know, so our tool path's a little bit wrong. We don't care. And like you can also see like how rough these surfaces are. So they just rough milled it, but then they did better down here. I don't know why they did that. They could have done a better job on that. And again, you can see one of those same little toolpath mistakes over there, whereas all the rest of these are done this way. So little inconsistencies like that, and that's a fairly common thing out of China. Make the outside pretty, and then, you know, kind of skimp on the inside. And, well, the outside is perfect. So that part looks great, and I can see why people like this, because, you know, it's very attractive. You know, I think it is too. So, yeah, that's a fairly common thing, you know, cut corners where people supposedly won't see them. All right, on this armature, or the stator rather, you know, again, the winding binding is not very good. You've seen this already. This is subpar, not acceptable. Every time you go over a bump, take a jump, hit a curb, whatever, your windings do this. They move like that. And you can see that's all over here. You know, this part I've obviously cut the bindings off so I can measure the strand count, and I'll get to that in a minute. But yeah, none of this should have ever happened. And I haven't unbound any of this part, so it should be moving exactly like it was in the factory. And you've already seen this on camera once before. So when they move like this, yeah, the strands are rubbing against each other, friction, and they're slowly wearing through their insulation. So you don't want that to happen. And it's going to eventually wear through the insulation and then create a winding short. Exactly how long that's going to happen for you, I don't know. It may not ever happen for everybody, but I can tell you that you increase the chances of motor failures for this very simple reason. And it's a very simple, super simple thing to fix. Which you have seen me do on like the QS165 and the TP128 motors. You literally just bind them up properly and then you put shellac on them. And there's no shellac anywhere in here, and obviously the bindings are not very good. So Moto, you really need to fix this. This is not acceptable. It's definitely way too loose, and I will do another video later where I take all this off and I will rebind it myself, and I will add shellac to it, and then I will show you what not moving looks like, because when I'm done, it flat out will not move at all. So yeah, this is meh. Not okay. That really sucks. That's going to be a failure point for quite a lot of motors. All right. There are a couple things that I discovered that I really like, and good job on that Moto. So this is one of them right here. So you can see all of these strands right here, and that was under that piece of heat shrink. I cut it off because I wanted to see how this was. And so this right here is all the strands coming through here and inside the windings. Literally, they brought the strands right out to the ring terminal. This is exactly how I do it on motors. This is very good. There's no extra parts. There's no joints anywhere. You literally bring the wires straight out to your ring terminal. And if the strands are nice and thin, you have lots of flexibleness in the cable. You've minimized losses, and this is actually a lot cheaper than ending right here and then connecting a piece of silicone or Teflon wire out to bring it out here, and it's lower losses. So it's a better way of bringing your phase ends out than doing it the other way, and it's cheaper and it costs less. Less labor, everything. No extra parts to buy, no soldering work. You literally do it right here and you're done. So it's a better way to do it. And I saw that, I was like, oh, well, cool. Good job for you, Moto. That's how I do it too, because that's the best way to do it. Yeah, so definitely like that. These little grommets on here, this is a fairly expensive part right here. And so this piece threads into the aluminum, and it's got an O-ring behind it to seal it up in there. And then you have this nut, and then you have this little plastic outer sleeve right here. It's a compression fit, and it squeezes around the actual wire. And then inside that, this black part, that is a silicone grommet, which comes up through here as well. So when you tighten up the nut, this plastic part squeezes the silicone, and it compresses all the stuff together to make a really good watertight seal. It's a very reliable way of doing things. When I had the chance to use these things, I used them myself. And like right here, you can see this little thin spot, and that's where that part right there is clamping around the strands of wire and the heat shrink. And it makes a great watertight seal that's mechanically very secure. When I saw that, I was like, oh, wow, check that out. It's a fairly expensive connector that's very reliable and does its job very, very well. Good job, Moto. See, I'm not really a hater. When you do things right, I do praise you for it. When you do things wrong, I do say that it's wrong or bad. So, yeah, this is not acceptable, so I'm saying it again. This is bad, Moto. This right here, how you did your phases, these little grommets, that's really good. Notice it's both. It's not just hate. It's not just bias. It's both. All right, let's talk about the next thing here. I have counted these strands, and each one of those is 0.37 millimeters. You can do the conversion and find out what actual gauge of wire that is, but there are 41 strands here, and this is 2 Y winds on this motor, so that's really 82 strands. And if you find out what the AUG is, then you can find out what the copper cross-section area is, and then you can do the math to figure out maximum possible amperage through those 82 strands of wire. And that may be where Moto gets that pie-in-the-sky amperage rating, which they have now taken down from their website because I went looking for it, and it used to be up there. In fact, the wattage isn't even listed up there anymore. So yeah, it used to be there, and I'm pretty sure it said 32 kilowatts. And I'm going to say that probably those numbers are probably based on the copper cross-sectional maximum amperage that you can get. And it's not realistic, because you'll never get that. You'll get some percentage less than that. So yeah, I'm guessing that's where they got those ridiculous numbers they had posted before. So yeah, another thing I didn't like, and I don't know how this shows up in camera. Where is a spooger? There we go. Right there. So you can see right there. Yeah, here's another one right there. Yeah, 2 of them right there. There was another one I saw too. That was escaping my view at the moment. It's here somewhere. Oh, there it is. Can't really see it so much. So right down here underneath those strands, yeah, there's another loop right in here. It's just kind of like all kind of twisted together. You probably can't see it so well on camera. Anyway, a bunch of places where, you know, massive gap in the strand that shouldn't be there. You should make sure that that doesn't happen. Looseness like this is, it just shows low attention to details as you're winding the stator. And that's easy enough to find. Every time you pull everything through, you just literally pull in all the wires so that they all come back out and pull all that slack out of things. And then you do the next loop and you do the same thing again. You pull in all the strands to pull out all the extra slack so you don't get little loops and stuff, you know, like that. Anyway, yeah, that's not super cool. Yeah. I will solve this problem by just binding everything up, and that's going to make that a lot better. But yeah, you just make sure that you pull all your strands tight, and then you don't have those really loose loops like that. Anyway, yeah, I saw that, I was like, yeah, that's not super cool. Other things like bringing out the phase wires right out to your ring terminals, that's pretty good. That's pretty damn awesome. This is exactly how I do it. The ring terminals are sort of crimped on, so you can see that dent right there. If you're going to do ring terminals, you're going to crimp them, you want a hex crimp, so it crimps from 6 sides and squeezes everything all together from every direction. Pair of pliers, I don't know how they did that, but anyway, yes, this is far less effective than a 6-sided crimp. Yeah, definitely like seeing 6-sided crimps, and this is going to be less good. But there is some solder between the ring terminal and here, not a lot. So that's going to kind of mitigate that in some ways. But if you're going to crimp right, and, well, they didn't. Yeah, they did it the easiest, cheapest way they could with a pair of vice grips or pliers or something, just to get one little dent in them. And that's also how these other ring terminals are as well. So good and bad in the stator. Some things I like, some things I don't. This is good. Like these grommets, those are great. Like how the phase ends literally come right out to the ring terminals. That's good too. Really loose winds, you know, terrible binding. That's not very good. That pretty much sucks. No shellac on anything. That pretty much sucks. Yeah, that part isn't so good. Yeah, gaps in your armatures. That just shows absolutely lack of concern for quality control. Yeah, that's not very good. Chinese bearings on a $1,400 motor. Yeah, that's not very good. Using balancing putty on a $1,400 motor rather than grinds. Again, that's just, you know, cheaping things out, not doing a very good job. But, you know, it's got this fabulous shaft on here. This is not made by KO Moto. I am dead sure of that one. It's just simply way too good for their level of manufacturing. All right, so let us pull out some of my so-called smoke and mirrors, you know, meters, and start reading some stuff. And push this back a little bit and grab the Gauss meter so we can look at magnetic strength. Set that to Gauss. And here is the armature. And I've obviously labeled south and north on here already. And here is my little north-south detector. South, north, right? Oh, button's not working. What happened? Well, it just quit. There we go. South, north. Okay, so here is the sensor for my Gauss meter. And let me pull the lid off. So a little T for top on there, so that means don't put that down, put this side down. And let's see what we get here. So the corners of the magnets, like you can see right there, that's like the strong spots. And I need to lay this down flat on here. There we go. And yeah, I've measured about 3,700 Gauss right at that corner of the magnet. And yeah, you see, there we go, 37. We get down towards the middle and we get about 1,500 Gauss. Yeah, there we go, 1,550, 1,540, it's about right. Get over to the other side, should get up to about like 3,700 Gauss again. And come on, really? Oh, get over there a little bit. Yeah, I'm just reading a little low. Oh, there we go. I just saw like I think I did. It was really quick. I thought I saw 36 or 37. Yeah, that was kind of weird. I'm right over that corner. Well, there's 31. But yeah, for some reason that one's reading a little low. Maybe this magnet right here just never got magnetized particularly well. And of course, right across the top of the bridge, you know, between the two magnets, that's where they cancel out. We should see pretty low. Yeah, I saw like a 0.09 there or a 9 rather. Then we come over here to this corner. Yeah, there we go, 32. And there we go, 34, 33. Yeah, so somewhere's right around there we should see like, yeah, there we go. There I saw 3,600 Gauss. Oops, same thing. Get over here. Should see about like 1,500 in the middle. So, you know, this is pretty typical for an IPM motor, right? We've seen this before like on the QS 165s and on the TP 128s. You know, you get about the same Gauss levels. So let's turn that off and set this aside in the armature side. And let's pull out some more smoke and mirrors, you know, aka actual test meters that read real live values of things and see what that is. So, yeah, you can see here's your 3 phases. Let me get that out of the way so it doesn't interfere with anything. And here is my milliohm meter. Set that up right there. And this should be zeroed, but we'll check it real quick. Or pretty close to zeroed. And yeah, I'm going to call that good. Let me unclip them again, redo it. That way I can check several times. Yeah, that's not too bad. It's a little bit high on that one. Try this again. Yep, there we go. That's pretty good. All right, so let's see what I get here to here. And I believe I was getting about 6.5. Yeah, 6.8 milliohms. That's not bad. And from here to here, probably about 6.75 milliohms. From here to here, 6.67, 6.69. Yeah, that's pretty good. And backwards. 6.79. Yeah, these are the same kind of numbers that I was reading that I wrote down. So those are pretty consistent results. And 6.66, 67, and one last reading right here. Yeah, this is not smoke and mirrors, folks. These are real test equipment devices. You know, they read what they read. That's all that is. So 6.61 milliohms. So the resistance in here is fairly low, which is good. It just means resistive losses are not going to be that great. Or you're always going to have losses. It just is how it goes. So the lower that resistance is, the better off you are. And I would call 6.5, 6.7 milliohms pretty decent. But then again, you know, it's got 82 strands of probably 22 or 24 og wire in parallel, so the resistance ought to be pretty low. Looking at this, it looks like it's 5 turns. Don't quote me on that because I can't really be sure without like unwinding the motor, which I did to the TP128, and now I can say for a fact that that's 5 turns. But this here, you know, it looks like it could be 5 turns, and that's about as good as it gets there. So inductance, so from here to here, let's see what we get. Yeah, get out of my way. Move that out of the way. No, stop touching. There we go. So 119 microhenries, and I have 124 written down. And we've seen this vary a little bit before. From here to here, yeah, 122, and I have 124 written down. Yeah, then dropped to 116. Oops, leave that one on there. From here to here, I show 118, and I have 124. Oh, dropped to 113. So yeah, there's LCR meters are never like exactly exact devices. There's always some variation a little bit. You get RF interference, things like that in them. You know, this is effectively a coil, right? Duh. It's going to pick up RF interference. It's going to make the meter read a little bit wrong. So on that one, you know, now I'm going backwards, right? I was measuring 119. Now it says 115. And here to here. Says 124. Yep, that's what I got written down too. And here to here, 126, 122, and I have 122 written down. So yeah, that's pretty close to what I read before. So that's not too bad. So something in the range of about 119 to 126 microhenries of inductance in here. Anyway, that will help some people out who are doing like controller tuning. You know, if you like to have a VEST controller or anything that's properly FOC. With the full suite, you definitely need to know inductance, you need to know phase resistance, and, well, now you have it. So, yeah, not smoke and mirrors, actual test equipment, reading stuff for what it really is, and that's really all that is. All right, is there anything else that I need to show you before I let you go? Nope, I think that's probably the important details. Again, 41 strands, 2 Y winds in parallel for a total of 82 strands. 0.37 millimeters. Laminations are 0.35 millimeters. This is 50 millimeters tall. That ID in there is, what did I write down? 97.3 millimeters wide. This is, of course, you know, well, like right there, 50 millimeters tall. And this is 60 or 96 millimeters across either here or across those ribs. Either one I get pretty close to 96 millimeters. So 50 by 96 for that. Yeah, for a $1,400 motor, you should be getting a lot better quality than this. You shouldn't be seeing balancing putty. At least they did harmonically balance it, I'll give them that. You shouldn't be seeing Chinese bearings. You definitely shouldn't be seeing things like this or loose winds. Yeah, that's the monikers of somebody who is just raping you on price and doing a cheap job. You should get a lot better attention to detail for $1,400 than this. Definitely not Chinese bearings. Anyway, yep, that's it for this video. Hope to help some folks out. Take care. Talk to you later.